In this video, I want to explain how to draw Lewis dot structures. There are 5 basic steps to draw a Lewis dot structure. The first step is to determine the total number of valence electrons in the molecule. The second step is to determine how the atoms are arranged in the molecule. The third step is to distribute the electrons. The fourth step is to complete the octet of the central atoms with double and triple bonds. And the last and most important step is to verify the molecule is correct. Let's run through these steps with a couple molecules to get comfortable with how these steps work. We can start out with formaldehyde, which has a formula of CH2O. So in the first step, we have to determine the total number of valence electrons in the molecule. We said the molecule was CH2O. We can find the total number of valence electrons by looking up each element on a periodic table. The group number that the element is in is the number of valence electrons. So, for example, carbon is right here, and it's in group number 4A. It has 4 valence electrons. And there's 1 carbon, so for the carbon element, we would have 4 valence electrons. And hydrogen, it's in group 1A right here, so it has 1 valence electron. And there are 2 atoms, which would give us 2 valence electrons. The next element is oxygen, which is right here in 6A, and there's 1 oxygen. There's 6 valence electrons, and there's 1 oxygen. So that would give us 6 valence electrons for oxygen. To find the total number of valence electrons in the molecule, we just add up the valence electrons for each atom to get the total. 4 plus 2 is 6, 6 plus 6 is 12. So we would end up with a total number of valence electrons of 12. Step 1 is complete. In the second step, we determine how the atoms are arranged in the molecule. A couple guidelines to go by is to put the lowest electronegative atom in the center, and to also remember hydrogens are always on the outside of the molecule. So the formula was CH2O. Looking at the electronegativities, carbon has an electronegativity right here of 2.5. Hydrogen has an electronegativity of 2.1. And oxygen has an electronegativity of 3.5. So looking at the electronegativities, we can see that hydrogen is the lowest electronegativity, but right here it says that hydrogen is always on the outside of the molecule. Whenever a statement has words like always or never, does not happen very often, so when we do see statements with words like this in it, we should pay attention to it. This says that hydrogen is always on the outside, so this cannot be a central atom. So the next in line would be the carbon. So we can put that in the center, and we can put hydrogen on each side of the carbon, and we can put oxygen above the carbon. So the arrangement of the molecule would have the carbon in the center, the hydrogens on the outside of the molecule, and oxygen on the outside of the molecule since it's the highest in electronegativity. Now let's move on to step 3, where we distribute the electrons. First, we connect the atoms in the molecule by placing 2 electrons between the atoms to present a bond. Once that's complete, with the remaining electrons, we complete the octet of the atoms on the outside of the molecule. We don't have to worry about hydrogens because their outer shell is complete with 2 electrons. So that leaves us oxygen, and we had 12 valence electrons. We used up 6 valence electrons connecting the atoms. So that would leave us 6 valence electrons to distribute on oxygen. And now the octet for oxygen is complete with 8 valence electrons. Step 4, we complete the octet of central atoms with double and triple bonds. If the central atom or atoms do not have a complete octet, move the electrons that were distributed to the outer atoms as shared electrons with the central atoms to form double and triple bonds until the central atoms have reached a complete octet. So evaluating each atom on the molecule, we can see that oxygen has a complete octet with 8 valence electrons around the oxygen. We have 2 bonding electrons that connect the oxygen and the atom, and we have 3 lone pair electrons that surround the oxygen. Which would give oxygen a complete octet. Hydrogen only needs 2 electrons to fill their outer shell, and each hydrogen has 2 electrons, so they're complete. So right now the only atom that doesn't have a complete octet is carbon, and we do that by moving a pair of electrons from the oxygen to form double bonds between oxygen and carbon. After we move the lone pair of electrons from oxygen, into bonding electrons between carbon and oxygen. Carbon then reaches a full octet with 8 valence electrons. Carbon has 2 electrons bonded with hydrogen and 4 electrons bonded between oxygen and carbon that are double bonds. A feature that we can take advantage of with bonding electrons is that the bonding electrons are counted towards the octet with both atoms, not just one. When we have lone pair electrons, they only count towards the octet of the atom they're attached to. So when we took the lone pair electrons from oxygen and moved them into bonding electrons, carbon could then count those towards reaching an octet as well. So carbon has 2 electrons in between carbon and hydrogen. It has 2 electrons in between the other carbon and hydrogen, and the electrons between oxygen and carbon can be counted as well. So that would give carbon enough electrons to reach 8 valence electrons. The last and most important step is to verify. The first is to make sure the number of valence electrons in the final molecule are the same as the total number of valence electrons determined in step 1. In step 1, we determined there's 12 valence electrons in the molecule. So we have 2, 4, 6, 8, 10, 12. So that checks out. And the last step is to make sure that each atom has a filled outer shell of 8 valence electrons, with the exceptions of hydrogen, as hydrogen only requires 2 electrons to complete the outer shell. First, we'll look at oxygen. Oxygen has 2 sets of lone pairs on the oxygen, and it has 4 bonding electrons in the double bond. So that would come out to 8 valence electrons. Carbon has a pair of bonding electrons in between carbon and hydrogen right here, and it has another pair of bonding electrons between carbon and hydrogen right here, and it has 2 bonding electrons between carbon and oxygen, which would give it 8 valence electrons. So this atom checks out. We said that oxygen checked out with 8 valence electrons. Each hydrogen only requires 2 valence electrons to complete the outer shell, and this hydrogen meets that requirement with 2 bonding electrons, and this hydrogen is the same, it has 2 bonding electrons. So all the atoms have filled outer shells, and this requirement is fulfilled, so we can say that step 5 is complete and the molecule has been verified.